Welcome to Microlecture 43. We're going to talk about a specific type of SN1 reaction, that of alcohols with HX. Okay, so let's do some examples of some SN1 reactions. And we're going to pay particular attention to the way that we're drawing stereochemistry in the product. What you're going to find for a motif for SN1 reactions is that they are often the reaction of an alcohol with a hydrogen halide, so HX. So for example, HCl. And when we're predicting the products, we want to show, well, this is a stereo center, so we want to show, do we make just the R stereo configuration, or is it S, or is it a mixture? And if you recall from the brief introduction to SN1 mechanisms, we form a mixture of products. And so we're going to both retain the stereo configuration at that site and also, with equal likelihood, form the inverted product with the opposite stereochemistry. And so in this case, what we would form is a 1-to-1 mix of enantiomers. And you also might recall the vocabulary word there, that this is a racemate. A 50-50 mix of enantiomers is a racemate. The mechanism proceeds to also produce water as a product, just FYI. And another example would be, so maybe an alcohol like this reacting with HBr. We would predict that the bromine would displace the alcohol in this SN1 reaction, and the resulting product could be drawn this way. Notice there's no stereo center. There's two methyls on that same carbon, and so there's really nothing to indicate in the way of stereochemistry for the product. Okay, so we'll get to the mechanism here in just a second, and we'll talk about the unimolecular reaction rate and how that plays into each of these examples as well. But first, let's just be thorough and cover sort of all of the scenarios. So another scenario would be this situation where we do definitely see a stereo center, and so we want to show how that's going to play out in the products. Remember that the nucleophile can approach the carbocation that forms through an SN1 mechanism from the top or the bottom, and so we're going to get a mixture of retention and inversion at that stereo center. So with equal likelihood, we would form this mixture of products. Okay, and then in this case, it's not a mixture of enantiomers, so that was the sort of big idea, is to be able to identify the relationship, the stereochemical relationship between the two products that are formed. In this case, you've got a 1-to-1 mix, but they're diastereomers of each other. All right, what that means experimentally is that, a racemate would be achiral overall. We would not have optical activity for that first set of products, because the two enantiomers kind of cancel each other out. Of course, when you don't have a stereo center, that type of product is achiral. So we've got that example. And then we've got the example where we do have a chiral product, because nothing ever changes about this stereo center up here. And so this is an optically active sample that we produce as a result of this chemistry. Okay, I wanted to remind you that the rate is just the rate constant K times the concentration of the substrate, if you will. I haven't really used that term substrate, but we were talking about alkyl halides before, and now we're talking about alcohols. So it's the species that is attacked by either the nucleophile or the base, right? That is the species that matters in the rate limiting step. So in these reactions, that species is always an alcohol. So when we're talking about the reaction of an alcohol and HX, then the rate, it depends only on the concentration of the alcohol. Level of substitution of the alcohol is going to be a huge factor in determining the rate of this type of reaction. So tertiary alcohols will react the fastest because they're going to make the most stable carbocation. So they'll react the fastest, and secondary alcohols will react next fastest, and primary alcohols do not react. Right, so just an example of a tertiary alcohol would be like this, secondary alcohol, something like this. Okay, primary alcohol, something like this. And I'll take you through a SN1 mechanism of reaction that involves an alcohol as a starting material on this next slide. Okay, so for the SN1 mechanism, let's start with this alcohol from our first example, and HCl, and show how these products form. What is the mechanism by which we're going to form this mixture of products we said that we were going to make. All right, so the first step is going to be actually activation of this alcohol, right? So the OH group can't just kick up and leave. It's not a good leaving group. It would generate something so incredibly strong, and that is hydroxide. And so hydroxide won't form, especially not an acidic solution, and this is HCl. Okay, so what really does happen here, instead of us just losing our leaving group as we saw in the first type of SN1 mechanism that we covered, is that our alcohol, again, is activated. That means protonated by the solution. So HCl is just H plus and Cl minus. And so we can pick up a proton from solution and generate our first reaction intermediate. Now we have a good leaving group, and that will be water when we kick it out. So in this next step, we can break that bond to give oxygen a lone pair of electrons, generating the carbocation intermediate that's going to get us to our product. All right, and so the last step is just showing that the chloride ion can come in for the attack. It can do so on the top face of this carbocation, which is flat, or the bottom face with equal likelihood. And so when it attacks, it has equal likelihood of forming either of these two products. What we're going to see here is an interesting looking reaction energy diagram curve. Okay, so first of all, we're going to start out at the energy associated with the reactant alcohol. And we'll have to overcome enough energy for that alcohol to become protonated or activated. And that's going to generate this intermediate right here, the protonated version of the alcohol. And then with enough energy, that species is going to lose water as a leaving group, but there's a huge amount of energy to overcome in order to get to that point where we have just a carbocation. So this is going to be our carbocation intermediate here, and then ultimately we're going to end up, after the chloride comes for the attack, we will form a product. So what we're seeing, if I label my axes to make a nice complete reaction energy diagram here, what we're seeing is that we have definitely a rate limiting step. That's the one with the highest activation energy. And that correlates with the second step, which makes sense because that is the loss of the leaving group to form the carbocation. We said that would always be our rate limiting step. In other words, the one with the largest activation energy.